Okay, so let's begin by stating the Erdos Gallai. Be a sequence of non-negative integers. Then D is graphic if and only if So this is a very different characterization than what the Havel-Hakimi is doing. It's a very different kind of characterization. It is not asking, so in philosophy as well as all workout, it's a very, very different kind of characterization. Havel-Hakimi is actually bypassing the question to a lower level. That is not what this is doing. You give me the numbers d1, d2, dn, this can be checked. You can check whether those inequalities are satisfied or not. Obviously, sigma di has to be even, that's clear, that's true for any graph. Out of this, it is easy to prove the necessity of this condition. Just take the set of first k vertices, v1, v2 to vk. Every vertex here, the edges that it sends out, either it could send out an edge internally inside A, and that is what is counted here. The size of A is k. Therefore, but you will be counting for each vertex because you are adding all these degrees. Therefore, it's k into k minus 1. In addition, there will be some things going to V minus A. Every vertex which is not in A will contribute something to the degree of a vertex in A. How much can it contribute? The jth vertex cannot contribute any more than dj, obviously, because its degree is dj. And there are only k vertices here, therefore it cannot contribute anything more than k. Therefore, the jth vertex can contribute at most the minimum of dj and k. That is true for every j here from k plus 1 to n. Therefore, this inequality is correct. That says that this condition is necessary. This condition really is necessary. So it's easy to see that this condition is necessary. Somehow it tells us that it's a fairly natural condition to have. What is not obvious, and in spite of simplifications, the proof of sufficiency is not easy. It is not easy at all. no matter which book you pick up, the sufficiency, there are trickeries involved in proving that those conditions are sufficient. Erdos Gallai conditions are sufficient. Therefore, we leave it at that. Necessity, as I just told you, is quite obvious why that condition is necessary. Because for a vertex in A, it can come in only two ways. It can go inside A, which is counted over here, or, and has to be counted two times, because once for this endpoint and once for that endpoint. Or it can go across that way, and those can be looked at by contributions from the vertices in V minus A. But a typical vertex there cannot contribute any more than this. It obviously cannot, its degree is dj, so it can contribute only up to dj. Also there are only k vertices, so it can contribute only up to k. So I must take the minimum of these two numbers and sum over all these. Therefore, this inequality is a natural inequality if I have a simple graph. Yeah? We are not looking at them. See, the way this is happening is k will keep increasing. This is a sequence of, this is a set of as many as n inequalities here. Is it clear? A will keep increasing, okay? And that is monoton decreasing, okay? So the earlier D's are bigger than the later D's, okay? Erdos was a mathematician with largest number of papers, probably to his credit, something like 1400 research papers, died more than 10 years ago now. And Gallai, incidentally, was a co-author. Several things to Gallai's credit. The president of the last ICM, Hyderabad, Laszlo Loash, did PhD with Gallai. Gallai was PhD advisor of Loash. I mean, it's difficult to say who is bigger name. Probably Loash has cut out a very big name for himself, probably even much bigger than Gallai. Okay, but Gallai was a very fine mathematician. So, so that is Erdos-Gallai theorem. And it's very different from Havel-Hakimi. It's very, very different kind of thing. We will not prove the sufficiency of Erdos-Gallai conditions. Okay. Now what we need to do is get into what are called directed graphs. So directed graphs are those graphs in which edges come with directions. These are actually required in many situations. Let's begin with some examples. So typical directed graph will look like this. There could be edges going in both directions, that's possible. Okay? This is more sort of real life situation than having undirected graphs. After all, graph theory, the frame that you make depends on what you want to do. What is it that you want to achieve through this?
What is the point of having a direction for a loop?
That is a good question. Direction for a loop most of the times is not really required, except when you are looking at topological questions. Okay? When the direction being clockwise and anti-clockwise, it does matter. For topologists, it matters. Otherwise, it does not. Okay, you're quite all right. unless you are looking at topological questions. Directions on loops don't really matter. Let's take an example. So, fixed natural number if A divides B, there is nothing in between. Such a thing is called cover. The standard terminology, this is called cover. Let's take a large enough example. Let's take, maybe this is smaller, n is equal to 12. So I am now looking at all the divisors of the number 12. What are the divisors of number 12? 6, 4, 3, 2. Anything else? 1, of course. Is that clear? So that is the directed graph that you will get. Take a slightly larger number like 36 and construct it yourself. Leave it to you. Work that out. 36 has more divisors. You will get a path here if the number that you start with is a prime power. If it is a prime power, then you will actually get a path. P divides P square divides P cube divides P power 4, etc. So path is realized by, directed path is realized that way. That's the only way. So you can of course change primes and you will get the same path. Other example is of course a set of subsets of a given set, finite set, ordered by inclusion. So power set, members of a power set ordered by inclusion, in which case also we ask for a cover property of the same kind. Therefore, it's not merely enough to say that A is contained in B. There should not be any set between A and B. Okay? There should not be anything which is between A and B. Let's work this out for this set of order 4. Then you have all sets of order 3, all sets of order 2, all sets of order 1, and the empty set. Also goes to 2, 4. 1 goes to 1, 2, 1, 1, 3, 1, 4. 1, 2 is in 1, 2, 3. 1, 2 is in 1, 2, 4. 1, 2 is, that's all. So 1, 3. 2, 3. 2, 4. 3, 4. Yeah. This kind of picture is what is called Hasse diagram. The very it's called Hasse diagram. You may have heard this term. So this is what is meant by Hasse diagram. This is not just of interest only for graph theorists or combinatorialists. These objects are of interest for general mathematicians. There are groups acting on these, etc. So this is a very nice group acting. Alternate description of this is through binary words. So let's, it comes to doing the same thing. I take binary word of length 3. This and this are equivalent. So this is what is called the Boolean poset, Boolean partially ordered set, Boolean lattice. I didn't draw the directions there. You can represent a permutation. You can in fact represent a function. You can represent a function by what should be called functional digraph, functional directed graph. So take a finite set. If f of x is equal to y, then you draw that edge. Example, so functions can be represented by directed graphs. In particular, if you have a finite set and a function which is bijective on a finite set, then it's called a permutation. That's exactly what we mean by a permutation. Permutation is a bijection on a finite set. So if you have a bijection 1 to 2, 2 to 3, 3 back to 1. The picture with regard to permutation will be, it will be disjoint union of cycles. Those are exactly what are called cycles of the permutation. Those components there are exactly what one calls the cycles, in the standard sense of permutation. 1 to 2, 2 to 3, 3 back to 1. So it's a graphical representation. Directed graphs are used in other areas such as Markov chains, finite automata. Finite automata is a very big thing. We have no time to get into that, but it's worth. Finite automata is beginning of computer theory. People who look at so finite automata are based on finite automata is a very elementary machine. It's a very elementary machine where there are these vertices, nodes are like states. So these are states using a word, using symbols from a word you can move from one state to other. Certain states are declared. There has to be a state which we call the initial state at which the things begin, and there is a state at which they are supposed to end. So if your word ends at that particular state, then it's there in the language. Otherwise, it's not there in the language. So finite automata define a language. Those are called regular languages. They are called regular languages. It's a considerably more difficult thing to say what regular languages are. I will not define that here because look up some book on computer theory. There are regular languages come from what they call regular expressions. Regular expressions give rise to regular languages. Okay, and it requires quite a bit of an effort to say that there are even non-regular languages. Okay, so there are automata that cannot recognize some language. Okay, so this is quite a big area, and then if you cannot really take into fold all the theory that you would want to look at, then you improve your model. Then you actually enlarge your model. So finite automata which are very elementary then in turn give rise to what is called push down automata. This is what they call push down automata. So they work on the principle in data structures what is called stacks. Okay, so this will require very several lectures to get into this, so we will not get into this. But automata theory does require some idea of directed graphs. We'll look at something which is elementary but quite interesting. There are a number of games that require knowledge of directed graphs. I don't know if you have played such kinds of things. So let me stipulate one game for you. So there are two players going to play that game, and like in chess game, but this is much easier than the chess game. First player is A, then B, then A, then B, etc. This is typically what happens in a two-player game. So the simplest game I want to describe to you is player A starts with a number which is between 1 to 10. Okay? Then player B adds to it a number which is again between 1 to 10. For example, player A can start with 5. Then player B adds something which is between 1 to 10. Therefore, the total is what would be specified. He has added 6 here, and therefore using 6 is, then player A is free to add any number which is again between 1 to 10. Therefore, etc., etc. The first player who reaches 100, he is declared the winner. Okay? Have you played this ever? Some of you may have played this. Have you played this? No? Or you want to play it with me? I can, we can try it out. Yeah, who wants to begin? You want to begin? Huh? Or you want me to begin? Sorry? Okay, I'll begin. Okay. Okay, I say 5. How much do you want to add? You added, okay. So okay, all right. So, okay, all right, then I'll stick to that. Okay, just for the heck of it. 20? 27. 38. Huh? 50. 65. 87. 99, then I say 100. The first player who says 100. First to reach 100 wins. Yeah, so it's clear that somewhere I calculated it mentally so that I can get to 89. So that is the whole point here. That moment I get to 89, no matter how clever you are, it's irrelevant in fact. What you say after 89, it's absolutely irrelevant. Okay? I can jump to 100 very coolly. So my saying 89 assures a win for me. Okay? Now I just have to work it out so that I can reach 89. So again going one step backwards. Okay. So really speaking, these things, the initial part here is actually presuming that you did not have knowledge of how to solve this. I just randomly made those numbers, but when it came to towards the end, I was being cautious. Okay? If someone knows how to play this game, he should begin with 1. He should actually begin with 1. He is assured of a win. Because from 1, no matter what you say, I go to 12. Whatever you add, you can go only up to 11. Therefore, I can go up to 12. After that, whatever you add, I go to 23, then 34, 45, 56, etc., etc. And that assures me a win. So these numbers for this particular game, these are called kernel. This is the definition of kernel of a game. Okay? These are called kernel vertices. So these are in some sense good vertices. These are good numbers. I have a prior knowledge of what good numbers are. How are good numbers found out? Good numbers are found out by, as one of you just said, this is found out by a technique, what is called backtracking. If I have to win the game, I cannot begin here, I should rather begin there. Backtrack. Look at the hypothetical winning position, how you will get to that, etc. So that idea is called backtracking. You have to, these games are analyzed by using backtracking. So let's make a few definitions. You could have drawn a directed graph here. What is the directed graph? Directed graph is from A, you have a graph to A plus, you have an edge from A to A plus I, where I takes values from 1, 2, 3 up to 10. It will be a bit quite cumbersome to draw this entire graph, obviously, 100 vertices, but it's clear what that graph is. Then by kernel, what I mean is, set of vertices such that from one kernel vertex you should not be able, if I am at a good vertex such as 67 or 78, you should not be able to go from kernel vertex to a kernel vertex. Idea is very simple. From kernel you can only go out of kernel. So I compel you to make a bad move. Is that clear? Making certain that I can make a good move. There does not exist an edge of the form xy. You should not have an edge that goes from x to y. Otherwise, from one good vertex that I got, you will also move to a next good vertex. But that is not possible from 67. You cannot really get to 78. I ensured that. That's the idea of kernel. 2, for every z which is outside, there is an x in K such that Zx is an edge. All such kinds of games have a name. They are called progressively finite games. So progressively finite game is played between two players. Roughly the idea is can proceed in only one direction. No going back. Cannot pass. Is that okay? So it rules out large number of games. For example, some of you may have seen either you play or your dads play or your granddads play a card game called bridge. Have you seen people playing bridge? Yeah, there is a, so you distribute 13 cards to each one of the 4 players. There is a, very seriously they will look at their own cards, and then there is a bidding round. That someone begins by saying 1 heart and the next person says 2 spades, etc. But you see, there are also rounds where the first person says pass, the next person says pass, and all the 4 pass. This is perfectly all right with a game of bridge. It is just dissolved, okay? Then you distribute the cards again, shuffle them and distribute them again. So pass is quite all right in game of bridge. It is not okay for a progressively finite game. You cannot sit on a position. Is that clear? You have to move. You have to move further. You cannot repeat a position. No going back. Therefore, the game of chess is not progressively finite. You can take out a knight and put it back again. Only pawns move in forward direction. All the rest of the pieces can also move backwards. So chess is a far more complicated game than a progressively finite game. Tic-tac-toe would have, tic-tac-toe could be analyzed perfectly, yes. Quite some time back in 1930s, this person called Sprague, he came out with a theorem that said that every progressively finite game has a kernel, okay? The whole crux of the matter in winning a progressively finite game is to be able to find its kernel. If you can find its kernel, you're through. Because then the strategy is quite outlined. What to do is very clear. That sort of assume that you know the kernel and your opponent does not know the kernel, then you are quite well off. Unfortunately, that proof of that theorem is like it's like a meta statement. It doesn't tell you how to find that kernel. For each game, one will have to make efforts to find the kernel actually. In principle, every progressively finite game has to have a kernel, but if you have to find it out actually, it is not very easy to do that. For example, if I change this game that we just played here, think about it. You can add any number from 1 to 10, but you cannot add 5. This is this is a progressively finite game. Addition of 5 is not allowed. Okay? How would you go about playing this? Okay, for example, that just means that if you are on 95, I cannot say 100. That is not all right. Okay? Etc. So, yeah, you think about it. You can add any number from 1 to 10, but not 5. Okay? Addition of 5 is not allowed. So progressively finite games, the example I gave was the simplest by far. They can be made quite complicated. You cannot add multiple of 3. You cannot add a prime number. Is that clear? I mean, I can make them as complicated as possible. And in each case, finding a kernel in principle should be possible. But in actuality, when you have to find out the kernel, it is not very easy. It's not very easy to find the kernel. All this is done by backtracking analysis. But it's not a completely trivial job to find that kernel. One of the examples where this actually can be put in practice is the game of NIMS. Have you played the NIM game? NIM game works with this idea. NIM game is a progressively finite game. You have a certain number of chips. You have certain number of heaps or piles. So the first heap has 5 chips in it. Second has 3. Third also has 3. The fourth has maybe 4. Fifth has only 1. What is it? So there are as many as 5 heaps here. 5 piles, and I have to, players take turns. A and B take turns removing any number of chips but from the same pile. You have to remove, I am allowed to remove any number of chips. I can remove all the 4 from the 4th pile, that is okay. I don't have to. I can remove only 1. Though of course, as I said, being progressively finite, you cannot say pass. Okay? You can't say that I don't want to remove anything at all. Who is the winner? Winner is the person who removes the last chip. The person who removes the last chip is the winner. Okay? This is a progressively finite game. This is an NIM game. NIM games have very well defined kernel. It can be found out, but requires deeper mathematical analysis. Slightly deeper mathematics is required. Yeah, does someone want to play that? Huh? Try. Yeah, so you want to start? Yeah, go ahead. What do you want to remove? Huh? Yeah, go ahead. Remove the last chip? Remove? Huh? Okay, now you have to come to an agreement. What do you want to do? Huh? One chip from the first. Okay, all right. So that is gone. I removed one. What do you want to do now? Remove? Remove 3 from the first one. Yeah, quickly. We can't waste time. Yeah. Remove. Remove. Second row entirely. That's fine. So there is clearly a design in my mind. I'm working with a certain design. So there is a strategy for winning a name game. It's a very well analyzed game. All name games are quite well analyzed. This depends on what is generally called digital sum. Okay, if time permits, not today. Sometime if we finish the things, I can describe how name game can be played. But you can also look up literature how to play a name game. And once you know how to play it, maybe you can play with your friends who are not in this class or siblings. Try to impress them or whatever. Okay. A drudgery of graph theory that we have to get into here. Definition. Out neighborhood of x. In neighborhood. Out degree. In degree. Now the idea of connectedness for a directed graph has to be done carefully. You may be able to go from x to some z, but you may not be able to come back from z to x. This is quite possible because you are talking of directed edges. These edges are directed. Therefore, one has to be very careful here. So D is called weakly connected. Or connected sometimes. And these terminologies don't agree in all books. If the underlying simple underlying undirected graph is connected. It is called strongly connected. if there exists a directed path from x to y. So what one can do here is a generalization of the idea of Eulerian. One now wants to have an Eulerian tour or Eulerian circuit in this directed graph. In order for me to have an Eulerian circuit here, what is required quite clearly, make sure you understand this quite clearly. If you have a loop like this, it contributes 1 to the out degree and also 1 to the in degree. Okay? That is contribution. It contributes two things, 1 to the out degree and 1 to the in degree. Just as for undirected situation, it is supposed to contribute 2. That's what we said. Then, an Eulerian circuit in a directed graph is a directed circuit D is called Eulerian. If it has an Eulerian circuit. Analog of Euler's theorem for directed graphs would be, so let's write this out. D is Eulerian if and only if underlying undirected graph has only one non-trivial component and for all x, the out degree is equal to the in degree. Whatever goes out I'll leave the proof of this theorem to you. It's very similar to the proof we made for undirected situation. You just have to be a bit careful. Which part is quite obvious? The necessity is quite obvious. If you have an Eulerian circuit, then take a vertex. Every time you enter that vertex, you exit that vertex. Therefore, each time you go out, you have to come in. Therefore, this equality must be satisfied at every vertex. It's a sufficiency part which is not obvious, that obvious. But work out, there are two proofs that we gave for undirected situation. So see how you can modify them to get the same thing for directed situation. This really has a fairly nice application, and it works like this. So I'll just describe this to you in a couple of minutes, and then we'll look at it in the next class. On a cylindrical drum, I want to write these numbers 0 and 1. So these are in a circular manner. How many are these? These are 2 square equal to 4. If you look at any segment of length 2, so what are the things that I get 0, 0. Then I get 0, 1. Then I get 1, 1. Therefore, I get all of them. If I demand that I want to have every 3 segment, all possible 3 segments, then 2 power 3 is equal to 8. Therefore, I'll need to have a binary sequence with 8 symbols in it, in which you look at any 3 consecutive things, they should give me different things. So here it is. Here is one. Zero zero zero, 0 0 1, 0 1 0, 1 0 0, 0 no 0 0 1 is repeated, so this is certainly not good. No, so there is a mistake here. Yeah. No, so this is not okay. 0 0 1 is repeated. Such a thing is called a De Bruijn circuit. Such a thing is called De Bruijn circuit. And a theorem of De Bruijn says that you can do this for every n. You can do this for every n. For every n, you can write out a binary sequence of length 2 raised to n, such that if you take a consecutive segment, a segment that consists of consecutive n symbols, then you get all possible segments, which are 2 raised to n in number. You get all of them. Okay? So this is De Bruijn's theorem. This is called De Bruijn circuit, and that can be proved as a corollary to Eulerian theorem on directed graphs. So that is at least one use of looking at directed graphs. There is a point in doing that. There is a serious application. Besides, of course, as I told you, game theory, various kinds of things where directed graphs are actually required. You do require directed graphs. Okay, so we'll stop here for today. In any case, there will be no class next weekend. Okay, so presumably there will be one on 17, 18, 2 weeks from now.